it in a series fashion. So you could do series of parallel for this thing. But anyway, this is membrane separation. We basically have a two membrane system. We're going to be separating zero grade air. Zero grade air just means they put literally like the 21% oxygen and balanced nitrogen. Some air tanks are not all the same. Some of them are called breathing air. It's going to have some kind of moisture in it because you don't want to breathe dry air. Sometimes you have just regular compressed air. That's like something that tank can generate. You don't want to breathe that because you're going to have all of the hydrocarbon residues in there. So there are different grades of air. This one's basically just the nitrogen and the oxygen. Okay? We're going to run it through a series of membranes. They look like these. So it's almost like a shell and tube heat exchanger. So imagine this cap is on this side too. So they basically have this tube bundle, okay? And these little fibers are actually hollow. Okay? So they're hollow fibers. And then they're glued together so that whenever you come through the tube entrance, you actually have to go through the holes of the membrane, okay? So they go through, and then the oxygen is more selective, more permeable to these little membranes, so that'll tend to come out into the shell more than the nitrogen, okay? And this side's capped. So on the outside of this line, you would have a oxygen depleted side, right? So it's going to be enriched in nitrogen, higher than, what was it, 79%? So it'll be higher than that, nitrogen on this side. The shell side is going to start permeating this way and that way and this way and that way. And so this side is going to be much higher than your regular 20% oxygen or whatever, right? So your shell side is your oxygen enriched side, and the tube side is going to be nitrogen enriched side. Okay, so you should get it to separate. These things do a pretty good job. They do operate at fairly high pressures. So I believe this year you're going to be able to kind of pick. So your limitations are basically a minimum pressure of 20 psi and 100 psi. And then the flow rates are going to be anywhere between 1 and 12 liters per minute. Okay? So you're going to kind of do a design of experiments, which Dr. Ashley is going to talk about, where statistically you don't actually need to do every single combination of temperature, pressure. This is true for all kinds of experiments, right? You don't need to do every single combination to get essentially the same conclusions. There's I think there's even software that helps you do the DOE now, where you could actually selectively pick a minimized set of parameter combinations, and you can still essentially draw the same conclusions. There's a statistical way to do that. So y'all be able to do that and actually pick whatever operating conditions you want. Okay, but at a minimum, you're going to need, I think, 3 pressures and 3 pressures and 4 flow rates. 3 pressures, 4 flow rates, or I guess you could do 4 pressures, 3 flow rates. I think it comes out to 12 parameters, and you're going to be doing them in duplicates. Oh, that's something I didn't mention for the pumps. We're doing that 6 times for each pump. Sounds like a lot, but it's still going to be faster than all the other experiments because you can take the measurement. Yeah, sorry, I forgot about that. So for the pumps, we're doing them 6 times. When I say do them 6 times, let's say you're running through your pressures, right? Let's say you picked 17, 19, 20, whatever. You're going to do, as is true for every experiment we do, you're going to do all those parameters, and then you're going to go back and start at the beginning and redo them. You don't do the same one twice in a row. Why? If you set it up wrong for some reason, all of them are wrong, right? So like let's say you set it up for like 16 psi out there, okay? If you have set it up wrong somehow, then all 6 of your 17 psi conditions are all wrong. The chances of you doing that 6 times in a row every single time would be very small. So like if you do all the way to 20 and then come back, the chances of you getting 16 wrong again would be very small, especially over 6 times. So if you had any outlier or you did something wrong, it'd be very apparent which one you did. So it's a good way to kind of catch those outliers or a straight up mistake that was made. So don't ever do the same parameter twice. Same thing's true for this. So you have your 12 parameters. This one we only have time to do duplicates, but again, you do all your parameters first, then you come back and redo them again. Okay. So I have this all hooked up. Ali checked it already, so it should be ready to go. I'll basically come in. We'll set the air regulator to 120 psi. That's just to make sure we have enough pressure to get the 100. You always want to have a little bit extra on your gas regulator. So we need to make sure that gas regulator, the valve is the big black knob. We want to make sure that's turned to the left. Okay? Yeah. Do that before we open up the valve to the actual tank. Because the tank is probably at 2,500 PSI. Okay? So you don't want that fully open. You don't want the regulator valve fully open. Because that's going to just try to sit in the 2,500 PSI. So you always make sure you check that first. Then we can open up the tank pressure. Then we can set it to 120. Okay? And then we can open up the valve over here. We have a second regulator. So that one's going to be set at 120. That regulator is going to be the actual control regulator for the experiment. Okay? Can you hit the surge protector button at the top? Yeah. So before we send the pressure to the actual unit, we'll turn that on. We can just tear this. All right. So you can set the pressure with the gray knob, and then you can just read it off of this digital display. So the two parameters are going to be setting your pressure. Again, it's going to be somewhere between 20 and 100. And then we're setting the tube side flow rate as the operating flow rate parameter. Okay? That's not the only flow rate we're measuring, and they're going to be different. But the one that we're setting is going to be on the tube side. Okay? And that's this valve right here. So let's just walk through our flow path. So we can operate this thing in series or parallel, but we're only going to do series for this lab. Okay? So starting over there, the air. I got something a ruler or something I can play with. Is there anything around? You want to do the big arrow? That would be hilarious. It's fine. So the first part, the air is going to come out. Use this too, actually. So the air is going to first hit right here, or it can either go up or this way. Okay. So there's no valving or blocking on this way, so it's always going to come in through this first the entrance to the first membrane down here. These little valves up here, they're three-way valves. You can see they're kind of arrow-shaped. The arrow does not necessarily dictate the direction of the flow. What it does dictate is the opening on the valve. Okay? So this valve is pointing to the opening here. So there's a three-way valve, okay? This side, that's opposite of the valve head, is always going to be open. And either this side or this side can be open depending on where this arrow points. Make sense? Okay. So this points to the opening here. That means this side is closed. So you can have this open and this open. So flow can only come this way or that way. But it could be either direction. So if the air is coming from this side, then yes, it does point to the flow path. But if the air is coming from this side, which it will be in our case, the flow path is actually that way. Just don't get that confused, okay? The point is just the opening of the valve. Okay? So we want to go in series. So we don't want the air to come in this way and this way at the same time. So this configuration would be right. Because the arrow points to opening here, which means this is closed. The air is going to go up to this point and just stop. Can't go anywhere. So that's technically closed off, so that's good. The way that I like to remember it is that the series, this point on this corner and that point on that corner are facing each other. Okay? Because if you look at the actual flow path, that's the only way you can make it to where it's series. So the flow comes in from this side, it runs inside the tubes, and it comes out over here. And y'all, some of y'all in the back have to come get a better picture when y'all, once we kind of break up into our smaller groups. It comes out through this way, and it hits this valve. Again, the opening is going to be at the top. So the flow will continue all the way across. This is open now, and it goes in series. Comes out this side. This is kind of hard to see, but it comes out this side, and it comes out through here, and it comes in to your into this valve where we can set our actual operating flow rate. So this one we're going to adjust this. This one works right, tie that to Lucy, to increase or decrease our flow rate. So again, that's going to be 1 to 12 liters per minute. Okay. How we get it close? You're going to have to dance around with the pressure and the flow rates. What I mean by that is, like, if you increase the pressure, it's going to bump the flow rate up a little bit, so you have to come back down. So you have to kind of do this little dance move so you can get it exactly where you want. I would just get it close. Like, in the grand scheme of things, let's say you're at 12 liters per minute and you're at 12.06. It's 12. Don't kill yourself over it. The pressure is easy to adjust finally. This one, you might have I think even the pressure on the regulator kind of bounces a little bit too. So you're gonna expect some kind of like bounce in the air. It won't be completely steady, but it's gonna be average steady. Okay. So that was the tube side, right? So it comes out of here, goes around, and they all meet up. The shell side, the only place the shell side can come out is only one outlet for each one. So for the top diaphragm, it's this one, right here. Because you can, if you come look closer, you'll see some of the sides are plugged up. And this one for this side. So that's the only outlet for the shell. So once the gas flows through and it permeates the membrane, it gets in the shell, there's only one of these locations that they can come out. Okay, that's gonna be your oxygen-rich side. That's gonna be your shell side flow rate. So you'll notice that both this one and this one all meet up together, combine, and come out of the shell. Okay, so it's a combined flow. And you will read, so once it goes through our flow meters, okay, make sure you write those down. We have these little oxygen sensors that you can just plug in. I have them sitting out because before we start, we have to kind of zero them in on fresh air. And when I say zero, I mean 20.9, the actual air. Once we get them set up, we'll just tape them in like that. But while you're running, they'll run through the flow meter, run through past the sensor, and just come out, open air. But they read off these little oxygen meters, so we'll turn them on and calibrate them. You just take the oxygen percent directly off of it. Okay. So we're not reading nitrogen; we're just reading the oxygen. But we can infer. Let's see. You know what else? I wonder if we're doing the. I will talk about it later. It's fine. Anyway, so we have several things we're going to write down. So we have our pressure that we're setting, and we have a tube side flow rate that we're setting. But we have a shell side flow rate and 2 oxygen flow rates that we're actually measuring. Okay. Let's see. I have some backup sensors. One of them goes out, which they do over time. They get used up. It's basically like a little electrochemical cell on the inside, and then eventually you run out of chemical. Let's see. That's pretty much it. This one's pretty straightforward. Honestly, it'll probably be set up in the right configuration when you come, but assume that it might not be, and always check. You're gonna have to say that in your pre-lab presentations. How would you set it up? But realistically, when you get here, it's probably set up just to help you out with time and stuff like that. This little wire that feeds into the pressure display, that's a pressure transducer. That's the actual way that we measure the pressure. Something you'll need to note in your pre-lab. That is a actual part of the unit. You can ignore the other stuff, though. But the pressure transducer is how we actually measure the pressure. That's just the display. Okay. Some of the objectives you're going to be looking to observe, I guess, is you're going to be eventually determining mass transfer coefficients for this. This is basically a mass transfer lab. I'm sure you probably noticed we have a fluids, mass transfer. We're going to go to the heat transfer. So we're kind of covering most of the transport phenomena stuff this semester. So you'll be able to determine your mass transfer coefficients, your selectivity or separation factors, and then you'll be able to determine which operating condition is the optimal one. Okay. I think I already mentioned we're doing duplicates, and you guys are going to do a DOE to come pick whatever condition. So all lab groups probably have a different specific set of conditions, which is fine. Doesn't really matter. And then safety, I already hit home on we need to make sure we set that up properly, and I will absolutely come help you with set up the 120 PSI stuff, make sure that's all good. But just make sure that you're monitoring and watching me and make sure I don't make a mistake somewhere. Don't directly breathe from the outlets of the. So one of these is going to be nitrogen enriched, aka oxygen depleted. Mm-hmm. It will be depleted enough to where if you put your mouth on it and breathe in, you probably would black out. Okay. In the room though, it's all remixing back together to regular air, so it's not a hazard. Just don't breathe up on the thing. I don't think anybody did that, but I just have a note somewhere. If you feel dizzy, just leave the room. Just go step out somewhere else, get fresh air, right?
just switch to a different tube.
Oh yeah, but dude, breathe the other one. Yeah, read the other one for more oxygen. What else we got? Oh yeah. So this is just a general. Every time you work with compressed cylinders, I don't know if Dr. Pruitt ever show you the videos of what happens if you actually knock one of those things over. So while it's got 2,500 psi in this thing, it's essentially a missile that could actually go through cinder block walls once it gets going. That's a real thing. We need to make sure that clamp and strap is tight. It should be pretty good. If that thing were to not be, and it would fall over, because you get a good bit of leverage, since we have the actual, blanking on the damn thing, the regulator. Because you get a good bit of leverage on that valve stem, you could actually shear that thing off. There's no way to contain that 2,500 psi. It's just gonna go, and it'll take you with it if you want to hold on to it or not. So we need to make damn sure that thing is connected to that table at all times. And in general, when we move tanks and stuff like that, you never move a tank. This is not something you have to know, but this is just general safety that we always talk to our grad students about. We never move one of these things with the regulator still on it, and you always put the cap on it. Every time you have to move this, you always do it. You never leave it unattended without it being strapped to somewhere. So just make sure that thing stays on there, because somebody is going to have a bad day on the receiving end of that thing. All right.
Which direction do you think it would go?
Lucky for us, honestly, probably that way. And the good thing about that is that it probably won't go through the wall because it doesn't have enough room to get that momentum going. So like it would fall over this way or this way, shear off and go that way. So you're probably okay. Probably.
Or it wouldn't.
Huh?
Or it wouldn't.
Yeah.
It wouldn't. It'd be good.
Yeah, or it goes straight through. But I think we have a small enough gap to where it would probably wouldn't be able to go. I don't know. I never tested to see how fast it gets to speed, but it's pretty damn quick. Way back in the day, my dad, when he was in high school, they used to have a lot of